Somewhere in a spiral galaxy, nearly 500 million light-years from Earth, something is doing what nothing in nature is supposed to do. Every 16 days, almost to the hour, a burst of radio energy switches on, flickers for roughly 4 days, and then goes silent for the next 12. It has behaved this way since it was first caught by a Canadian radio telescope in 2018, and it has not missed a beat since. Astronomers eventually pinpointed its exact home galaxy, the nearest confirmed example of this kind of precisely repeating signal ever found. They ruled out coincidence. They ruled out equipment error. They tested nearly a dozen explanations, and still, after years of study, nobody can tell you, with real confidence, what is actually producing it. If a mystery like this is the kind of thing that helps your mind unwind, liking and subscribing costs nothing, means everything to this small channel, and helps more evenings like this one find you. Get comfortable now, and let your shoulders drop. In 3, 2, 1, liftoff. Somewhere above you tonight, well past anything your own eyes could ever pick out in the dark, a signal is arriving that has kept the same appointment for years. It does not arrive by accident, and it does not arrive at random. It switches on, speaks for a handful of days in a language made entirely of radio waves, and then falls silent again, and it has done this so consistently that astronomers can now tell you, weeks ahead of time, roughly, when it will speak next. If a lighthouse behaved this way, you would assume someone was tending the lamp on a fixed rotation. If a train behaved this way, you would assume someone, somewhere, had written a timetable and stuck to it without fail. This is neither. It is a burst of radio light reaching us from a galaxy so far beyond our own that the glow left its source before most of what fills your living room tonight had even been invented, and to this day nobody can tell you, with any real confidence, why it keeps such careful time. There is something almost unsettling about a natural event behaving this predictably, and something equally comforting about it, depending on how you choose to sit with the idea. Astronomers who spend their careers listening to the universe are used to a certain kind of chaos. Stars die in their own time, on their own terms, with no calendar consulted beforehand. Galaxies drift and collide across spans of time too long for any single human life to witness even the beginning of. Radio noise from the cosmos, on the whole, behaves the way static behaves. Random, textured, without any hidden order waiting inside it. So, when something in that static turns out to be keeping careful time, the discovery does not simply add one more fact to an already crowded field. It opens a much larger question about what kind of process, out among the stars, could possibly produce that kind of discipline in the first place, a question this video is going to sit with carefully, from the very first clue to the most recent research still being argued over today. To understand why that single fact has kept astronomers awake, it helps to understand what this kind of signal actually is, because it belongs to a family of cosmic events that has only been known to us for a little over 20 years. Astronomers call them fast radio bursts, and the name is almost embarrassingly plain for something this strange. A fast radio burst is a flash of radio energy, the same general kind of wave your car radio picks up or your grandfather's shortwave set once pulled out of the static, except compressed into a fraction of a second and carrying, in that instant, an extraordinary amount of power for something so brief. The very first one on record had actually happened in the year 2001, but nobody noticed it at the time. It sat buried in archived data from the Parkes Radio Telescope in Australia, a 64-meter dish that had been quietly recording the sky for years, until a researcher combing back through those old recordings finally spotted it in 2007, a spike in the data that did not belong to anything ordinary. That single strange flash, once it was confirmed, opened an entire new category of astronomy. It also opened a long stretch of doubt. For years afterward, some astronomers were not convinced that fast radio bursts were even real, in the sense of being genuine signals arriving from deep space. The suspicion was not unreasonable. The same radio telescope in Australia kept turning up other brief, strange pulses that looked almost identical to the original burst, and for a long while nobody could explain them either. Researchers eventually gave these imposter signals a name of their own, perytons, and spent years trying to track down where they were coming from. The answer, when it finally arrived in 2015, was almost comical. The perytons were not cosmic at all. They were traced to the staff, kitchen, and visitors center at the observatory, where a microwave oven opened a few seconds before its cycle finished, let out a brief burst of stray radio energy that the telescope's sensitive receivers happened to pick up. It is a small, almost funny detail, a great scientific mystery cracked open by someone reheating their coffee, but it mattered enormously because it forced astronomers to build much stricter tests for telling a genuine signal from beyond the galaxy apart from ordinary interference generated right there on the ground. A true burst from deep space shows up in only one narrow beam of a telescope's field of view, the way a single lit window looks different from the glow of an entire building seen from across town. A local nuisance, like a microwave oven, lights up every beam almost equally, because it is not coming from any one direction in the sky at all. It is simply sitting nearby. Once that distinction was firmly established, the doubt began to lift, and the hunt for genuine bursts from deep space picked up in earnest. Even once that particular confusion was cleared away, fast radio bursts remained maddeningly difficult to study, for a reason that had nothing to do with microwave ovens. The signals genuinely do come from far outside our own galaxy, in most cases from other galaxies so distant that their light and their radio waves have been traveling toward us for tens of millions of years at the very least, and in some cases for billions. A telescope catches one of these flashes, records it, and then has absolutely nothing left to look at, because the burst itself is already gone, vanished in far less time than it takes to blink. You cannot go back and take a longer look at something that lasted 1,000th of a second and will, in all likelihood, never happen again from that same patch of sky. For the first decade of this new field, that was simply the situation astronomers lived with. Every burst was a hit and run. You caught a glimpse of something extraordinary happening in a distant galaxy, and then it was over, before you could turn any other instrument toward it to learn more. Which is exactly why a source that kept firing from the very same spot, again and again, mattered so much the moment anyone noticed it. A repeater was not a hit and run. A repeater was a return customer. And for the first time, astronomers could actually plan ahead, point their instruments at a known patch of sky, and simply wait for the next flash to arrive on its own. Astronomers already had one example of a repeater to draw on by then, discovered several years earlier by a researcher named Laura Spittler and her colleagues, working with data from the Arecibo Observatory in Puerto Rico, the enormous dish built into a natural sinkhole in the island's interior. That source, first detected as a single burst in November of 2012, and confirmed as a genuine repeater in a paper published in 2016, had already proven that fast radio bursts were not, as a category, purely one-time cataclysmic events, the sort of thing you might expect from a star tearing itself apart in a single final act. Something about at least some of these objects could survive its own outburst and do it again. That discovery alone reshaped how the whole field thought about the problem, shifting some of the leading suspicion away from violent, one-time deaths and towards something more durable, something that could flare again and again across months and years without destroying itself in the process. But even that first repeater behaved sporadically, flaring without any obvious order that anyone had yet managed to find. And by the time a new discovery in the northern sky began drawing attention, the assumption among most researchers was that this newer source would eventually turn out to behave the same way. An energetic, unpredictable repeater, interesting in its own right, but not fundamentally different from the one example already on the books. There was a meaningful difference, though, between a source that repeats occasionally and a source that repeats often, and it was a difference that would end up mattering a great deal. The first known repeater flared only rarely, sometimes going silent for so long that researchers wondered whether they would ever catch it again at all, which made every single burst from it a small, hard-won victory. This new source, by contrast, seemed almost eager to be found. Once chime locked onto its location, fresh bursts kept turning up at a pace that made it, within a short time, one of the most prolific repeating sources ever catalogued. That difference in temperament, prolific rather than shy, was precisely what made a statistical search for hidden timing even possible in the first place. You cannot find a pattern in 3 data points scattered across 2 years. You can, if you are patient and careful, start to find one in 3 dozen data points scattered across a year and a half, provided you are willing to do the arithmetic properly instead of trusting your own eyes, which are notoriously bad at telling a real rhythm apart from ordinary clumps of chance. That hunt eventually led to a stretch of quiet, dry hill country in the interior of British Columbia, near the small town of Penticton, in a corner of Canada known locally for its orchards and its unusually sunny, near-desert climate, an unlikely landscape to find one of the most sensitive listening posts on the planet. At a research site called the Dominion Radio Astrophysical Observatory, radio astronomers have been listening to the sky from that same patch of quiet farmland for more than 60 years. The location chosen in part because the surrounding hills keep the site remarkably radio quiet, shielded from the ordinary electronic clutter of nearby towns and highways. The instrument that would ultimately catch tonight's signal looks almost nothing like the telescopes most people picture, the kind with a single giant dish that turns and tilts to chase a target across the heavens. This one has no moving parts at all. It is built from 4 enormous, half-pipe-shaped reflectors, laid side by side, each one roughly the length of a football field, and about as wide as a city street. And instead of chasing anything across the sky, it simply lies still and lets the turning of the earth carry the whole sky past its open face, morning to night, every single day. Astronomers gave it the name CHIME, short for the Canadian Hydrogen Intensity Mapping Experiment, and while it was originally built to study the way hydrogen gas is spread through the distant universe, it turned out to be extraordinarily good at something nobody had fully planned for when they designed it, catching fast radio bursts in the act, dozens of them, month after month, far more efficiently than almost any other instrument on Earth. The telescope itself is a genuine partnership built and operated by scientists from the University of British Columbia, McGill University, and the University of Toronto, working together with the staff of the observatory itself. And its nightly haul of data flows out not to one single research group, but to teams scattered across the whole continent, each one mining the same detections for a slightly different scientific question. Catching something that lasts only 1,000th of a second is a genuine engineering problem, not simply a matter of pointing a dish in the right direction and waiting. A conventional telescope, the kind that swings to track one target, might spend an entire night studying a single point in the sky and see nothing at all, because a fast radio burst can erupt from any direction without warning and vanish again before a human operator could ever react in time. Chime's answer to that problem was to stop trying to guess where to look and instead watch nearly everywhere at once. Because its 4 reflectors have no moving parts, the telescope is always staring at a wide strip of sky overhead, and behind it sits a bank of specialized computers, sorting through an enormous, continuous stream of incoming radio, static for the one particular signature that betrays a burst from far outside our galaxy, a flash whose higher frequencies arrive a fraction of a moment before its lower ones, smeared out ever so slightly by the thin haze of electrons that fills the space between galaxies. It is that same telltale smear, incidentally, that had once made a stray microwave oven look briefly convincing, and that now lets Chime's computers sort the genuine article from the noise of an ordinary evening, automatically, thousands of times a day. The scale of that sorting job is difficult to overstate. On any ordinary night, the telescope's computers examine a great many candidate blips, nearly all of them junk, a stray radar reflection, a passing satellite, a distant thunderstorm, anything with even a passing resemblance to the shape astronomers are hunting for. The overwhelming majority get discarded automatically within a fraction of a second, filtered out by software long before a human being ever lays eyes on the data. Only the rare handful that survive every test, the ones that show that unmistakable downward smear and appear in only a single narrow beam of the sky, ever make it into a scientist's inbox the next morning as a genuine candidate worth a second look. On a technician's screen, a genuine burst does not look like much, just a faint curved smear crossing a grid of frequency and time, there and gone in an instant, easy to miss if you are not looking for exactly that shape. But to someone trained to read it, that small curved smear carries an enormous amount of information. Its faint downward slope, higher frequencies first, lower frequencies dragging in a fraction of a moment behind, tells you the light passed through a very great deal of thin, ionized gas on its way here, far more than exists anywhere within our own galaxy. It is, in its own quiet way, a signature, proof stamped directly onto the signal that it began its journey somewhere else entirely, in another galaxy, long before it ever reached the 4 still reflectors waiting for it in the hills above Penticton. It was this telescope, watching patiently as the sky wheeled overhead, that first picked up a burst arriving from one small patch of sky in the northern heavens in the late summer of 2018. On its own, that single detection would have meant very little. Chime was already finding new bursts on a regular basis by then, and most of them behaved exactly the way fast radio bursts were expected to behave, appearing once, briefly, and never again. But within the following weeks, a second burst arrived from that same tiny patch of sky, then a third. The source was repeating, and while a small handful of repeating sources had already been catalogued by that point, this one kept flaring with unusual persistence, enough that the team monitoring the data began setting aside extra attention for it specifically. In the tidy shorthand astronomers use for record keeping, the source eventually took its formal name from the date woven into its very first entries in the catalogue, the 16th of September, 2018. A small administrative detail that would later feel almost fitting for a signal that would turn out to be obsessed with dates. Chime itself, for all its sensitivity, cannot narrow a burst's origin down to anything more precise than a patch of sky several times the width of the full moon, plenty good enough to notice that bursts keep arriving from roughly the same direction, but nowhere near good enough to say which galaxy, or even which star system within that patch, might be responsible. That kind of precision would require an entirely different approach, the sort of continent-spanning collaboration Marcotte and his colleagues specialized in, and it would not arrive for this particular source until later. For now, in those early months, all anyone could say for certain was that something out there kept firing from the same general neighborhood of sky, over and over, far more often than seemed reasonable for chance alone. Word of a new, unusually active repeater traveled quickly through the small community of scientists who study these bursts, and among those who took notice was a young astronomer named Benito Marcotte, working at the time at the Joint Institute for VLBI ERIC, a research organization headquartered in the Netherlands that specializes in linking radio telescopes together across entire continents so that they can act, in effect, as a single enormous eye. The institute where Marcotte worked exists for exactly this kind of collaborative hunting. Rather than operating a telescope of its own, it specializes in coordinating the work of dozens of radio observatories scattered across Europe and beyond, scheduling their joint observations and combining their separate recordings into a single, unified picture, a kind of clearinghouse for precision astronomy that few people outside the field have ever heard of, despite the outsized role it plays in nailing down exactly where, in the universe, a given signal actually originates. The technique is called very long baseline interferometry, and the idea behind it is almost beautifully simple once you hear it explained, even though the engineering required to pull it off is anything but. A single radio dish, however large, can only ever tell you the general direction a signal came from, the way one person standing alone in a field can point toward a distant sound, but cannot say precisely how far away it began. Link several dishes together, scattered across a continent or even several continents, and record the exact fraction of a second each one receives the very same signal, and suddenly, that single vague direction sharpens into something close to an exact address, precise enough, in principle, to pick out one particular building in a city on the far side of the world. Pulling that kind of precision off is never simple in practice. It means coordinating, observing time across several independent radio observatories at once, often in different countries, all pointed at the same patch of sky, in the same narrow window, waiting together for a signal that might not even show up that particular night. It is closer to conducting an orchestra scattered across an entire continent than it is to the popular image of a lone astronomer bent over a single eyepiece, and it takes months of planning before a single hour of actual observation ever begins. Marcotte's particular skill was not in finding bursts, but in hunting down exactly where they came from, a much harder problem than it sounds, since a burst lasting only a fraction of a second gives you almost nothing to work with once it has already passed. He had already spent years chasing this same kind of quarry, and when word came that Chime had turned up, an unusually persistent repeater in the northern sky, it was the sort of opportunity his entire career had been quietly preparing him for. What Marcotte and his colleagues would eventually accomplish with this signal, tracing it not just to a general direction in the sky, but to one exact galaxy, sits later in this story. But it is worth knowing now that the person who would finally give this mystery an address was already watching, already interested, long before anyone understood just how strange the signal would turn out to be. Through the rest of that year and into the next, CHIME kept its patient watch, and the picture slowly filled in. The source did not behave like a typical repeater, flaring sporadically whenever it happened to feel like it. Bursts kept turning up in clusters, several within a short stretch of days, then nothing for a longer stretch of silence, then several more. At first, this looked like ordinary unpredictability, the kind every repeating burst source seems to show to one degree or another. Nobody expected a natural process, however violent, to behave like a wristwatch. Stars do not explode on schedules. Black holes do not feed on a calendar. Even the most extreme and exotic objects known to astrophysics tend to behave the way weather behaves, wildly, in patterns you can describe only in terms of probability, never in terms of precise timing. So when researchers began quietly comparing notes about this particular source, the working assumption was simply that it flared more often than most, an unusually active repeater worth keeping under close watch, nothing more. Each morning, somewhere in that small circle of researchers, someone would check the overnight logs the way a person might check the mail, half expecting nothing and quietly hoping for something. More often than not, there was nothing new to see. But often enough to matter, there was another flash from the same reliable patch of sky, another entry added to a column that was slowly, patiently, becoming one of the largest single collections of burst detections ever assembled for one object. Inside the small working group tracking it, though, an odd feeling had begun to set in well before anyone had proof of anything. Scientists spend their careers training themselves out of hunches, and for good reason, since a hunch dressed up as data has derailed more than one promising career. But there is a particular sensation that comes from watching numbers accumulate on a page, night after night, and noticing, almost against your better judgment, that they seem to be clustering in a way ordinary randomness rarely produces. Bursts kept turning up in the same rough stretch of days each time the source reawakened, then falling silent for a stretch that felt, at a glance, suspiciously similar in length to the silence before it. Nobody wrote a paper about a feeling. Feelings are not evidence, and every astronomer involved knew it perfectly well. But the feeling was enough to make a few of them start doing something more rigorous than simply logging each new burst as it landed, quietly setting the accumulating dates and times aside for a more careful pass later. The kind of pass that could either confirm a real pattern or, just as usefully, prove that there had never been one at all. It is worth pausing here to appreciate just how unusual that kind of attention already was. By the time this signal turned up, astronomers had confirmed only a few hundred fast radio bursts in total, a tally that has kept climbing steadily ever since. Past 800 confirmed sources within the following few years, and higher still today, as CHIME and a growing number of other observatories around the world widened the search. Of all those bursts, the overwhelming majority, something in the neighborhood of 90%, had been seen exactly once, and never again. Only a small fraction repeated at all, and among those repeaters, only a handful were active enough to justify the enormous effort of dedicated, ongoing observation. Telescope time is scarce and expensive, shared among thousands of competing research projects around the world, and no observatory hands over weeks of continuous monitoring to a single target without good reason. This source earned that reason simply by refusing to stay quiet. Every time astronomers checked in on it, it had something new to offer, and that alone, long before anyone suspected any hidden rhythm, was enough to keep it near the top of the watch list. What nobody had done yet in those early months was lay the individual burst arrival times end to end and ask a far more specific question. Not simply, does this source repeat, but does it repeat in any kind of order? That question demands a very different kind of patience than simply logging each new detection as it comes in. It requires enough data, gathered over a long enough stretch of time, to separate a genuine pattern from ordinary randomness dressed up to look like one, because the human mind is famously eager to see rhythm and intention in places where none actually exists. Astronomers know this weakness in themselves better than almost anyone, which is exactly why they hold patterns to such a high standard before they will use a word like discovery. A handful of clustered bursts proves nothing on its own. It takes many cycles, tracked carefully and checked against the ordinary laws of chance, before a coincidence is allowed to graduate into a fact. By the start of the following year, CHIME had quietly accumulated exactly that kind of long record. Burst after burst, month after month, all traceable back to the same small point in the northern sky, each one logged with the precise date and hour it arrived. And the tally had already climbed past 36 confirmed detections from this one patch of sky alone, an unusually large sample for any single repeating source at that point in the field's short history. Nobody had announced anything yet. Nobody was certain of anything yet. But somewhere in that growing column of numbers, a pattern was already sitting in plain sight, waiting for someone to lay it out properly and see what it actually said. What changed everything from here was not a new telescope or some fresh discovery in another corner of the sky. It was simply time and patience, and the willingness to take a long column of scattered dates and finally ask them properly whether they were trying to say something. And once that work began in earnest, what it revealed would turn a merely active repeater into one of the strangest single objects in the modern sky, a signal that would go on to be traced across hundreds of millions of light years to one particular corner of one particular galaxy, and that would still, years later, be keeping its deepest secret entirely to itself. Asking a column of dates whether it is trying to say something turns out to be a very particular kind of exercise, more craft than magic, and it works something like this. Take every date on which the signal had fired, lay them out in order, and then try wrapping that entire timeline around a spool of some chosen length, the way you might wind a length of clothesline around your forearm in even loops. Guess the wrong length for that spool, and the marks representing each burst land scattered all over its surface, no two loops lining up with each other in any meaningful way. But guess the right length, the one that actually matches some hidden rhythm buried in the data, and something remarkable happens. Loop after loop, the marks begin to stack directly on top of one another, clustering into a single dense band instead of scattering randomly around the whole spool. Astronomers call this kind of test folding the data, and it is, in essence, exactly that, taking a long, one-dimensional strip of time and folding it back on itself, again and again at different trial lengths, watching for the one fold that makes everything line up. The list of candidate lengths tested was not short. A period could, in principle, have turned out to be almost anything, a matter of hours, a matter of weeks, some value with no obvious relationship to any calendar unit familiar to human beings. Rather than guessing, researchers tested a dense grid of possible lengths, methodically working through the range a computer could reasonably search in a practical amount of time, checking each one against the accumulated dates and asking patiently whether that particular length made the bursts line up any better than pure chance would predict. It is exactly the kind of exhaustive, unglamorous labor that rarely makes it into a headline. A great many individual tests, the overwhelming majority of them producing nothing more interesting than scattered noise, until one single length, and only one, produced a result striking enough to stop everyone in their tracks. That is essentially what the team monitoring this source did, once they finally had enough bursts on the books to make the exercise worthwhile. They took the accumulated list of arrival times, more than 36 of them by that point, and tested one candidate length after another. A few hours, half a day, a full day, several days, watching to see whether any of them made the scattered bursts collapse into a tidy cluster. Most lengths did nothing at all. The bursts stayed scattered, exactly what you would expect from a source flaring at random. But one length did something different. Wrap the timeline around a spool, 16.35 days around, and the bursts stopped scattering. They gathered, almost all of them, into the same narrow stretch of that 16-day loop, over and over, cycle after cycle, as if something out there really had been keeping to a private calendar the entire time anyone had been watching. It is worth being precise about what that number actually was, and about how carefully the astronomers who found it chose to present it. The period came out to 16.35 days, with an uncertainty of roughly 1/10 of a day in either direction, a small enough margin to make the result genuinely striking. But the researchers who announced it were careful, in their published report, not to overstate their own certainty. They noted plainly that the true underlying rhythm could, in principle, be some other value closely related to 16.35 days rather than that number exactly. The kind of ambiguity that can arise when you are trying to measure a repeating cycle using observations that do not, themselves, arrive on a perfectly continuous schedule. That caution turned out to be well placed and, at the same time, largely unnecessary. In the years since that first announcement, as more bursts piled up and other observatories around the world pointed their own dishes at the same patch of sky, the number held. Later refinements narrowed it slightly to somewhere between 16.33 and 16.34 days, but the basic finding never wavered. This signal, arriving from a source no larger than a city and sitting an almost incomprehensible distance from Earth, was genuinely repeating on a cycle you could set a calendar by. Accurate enough that once you knew today's date, you could predict, with real confidence, whether tonight was a night the signal might speak, or a night it would stay silent. The announcement, made in the year 2020, landed hard within the small community of scientists who study these bursts, because nothing quite like it had ever been confirmed before. Repeating sources were already known to exist, and a small number of them had already been catalogued and watched for months or years at a stretch. But not one of those earlier repeaters had ever shown anything resembling a true, measurable period, a fixed length of time you could point to and say, with the same confidence you might use to describe the phases of the moon, that the source will very likely go quiet now, and will very likely speak again in roughly 16 days. Fast radio bursts, whatever their true cause turned out to be, were widely assumed to come from violent, one-time or at least irregular processes, the astrophysical equivalent of a summer storm rather than the tide coming in on schedule. A genuine period changed the entire character of the mystery. It suggested that whatever engine was producing these bursts was not simply flaring whenever the mood struck it, but was being switched on and off again and again by some larger and more orderly process, working steadily in the background, a process patient enough and regular enough to keep exact time across years of continuous observation. Once the basic period was confirmed, the next task was to map out exactly what that 16-day cycle actually looked like up close, because a period on its own only tells you how long the loop is, not what happens as you travel around it. What researchers found, once they laid the bursts out against that 16-day cycle, was a source that behaved almost like a shift worker on a fixed schedule. For roughly 5 days out of every 16, the signal was active, capable of firing off a burst at almost any point during that stretch. Then, like clockwork, it fell silent for the remaining 11 days or so, and during that stretch, no matter how carefully astronomers listened, nothing at all came through from that patch of sky. 5 days on, 11 days off, over and over, a working pattern almost tidy enough to belong on a factory floor rather than in a distant spiral galaxy. And within that 5-day active stretch, the behavior grew even more particular. Roughly half of every burst ever recorded from this source did not spread evenly across those 5 days at all. They crowded into a much narrower slice near the middle of the active window, a stretch of only about 14 hours, well under a single day, as though the source had a favorite hour to speak even within its favorite days to speak. Picture what that 5-day window actually meant for anyone watching the sky in real time. For 11 days out of every 16, that particular patch of the northern heavens gave back nothing at all, a silence so complete that an observer with no prior knowledge of the pattern would have no reason to expect anything different the following night either. Then, as the 12th day arrived, the signal would begin again, the way a small shop in an old town might open its doors for only a few days out of every couple of weeks and pull the shades the rest of the time, faint bursts of radio light rippling out from a source hundreds of millions of light years away, arriving here on schedule while the patch of sky around it, full of other stars and other galaxies, carried on exactly as it always had, indifferent to the one small, precise clock ticking somewhere within it. That kind of layered structure, a long cycle containing a shorter active window, which itself contains an even shorter window of peak activity, is not the sort of thing nature tends to produce by accident. Genuinely random processes do not organize themselves into neat, nested stretches of activity and silence. They cluster unpredictably, they surprise you, and above all, they resist exactly this kind of tidy description. The astronomers who mapped out this structure ran the numbers again and again, testing whether ordinary chance could plausibly produce a pattern this clean, and the answer, consistently, was that it could not by any reasonable accounting. The odds of a source firing at random and happening to land, cycle after cycle, within the same narrow 5-day stretch of a 16-day loop were vanishingly small. Something was genuinely switching this source on and off, on a schedule, and by the early 2020s, that basic fact was about as close to settled as anything in this young field had ever been. Anytime a natural signal appears to repeat on a suspiciously tidy schedule, the first and most important question a careful scientist asks is not what could cause this, but could our own equipment be fooling us? Telescopes are complicated machines built from moving parts, scheduling software, and observing routines that themselves sometimes repeat. And it would hardly be the first time in the history of astronomy that a real-looking pattern turned out to be an artifact of how and when an instrument happened to be looking, rather than anything genuinely happening out among the stars. This is exactly the kind of caution that had already, once before in this story, been rewarded back when a whole class of imposter signals traced back to nothing more exotic than kitchen appliances. So before anyone was willing to call 16 days a genuine cosmic rhythm, they checked carefully whether their own telescope's daily routine could somehow be manufacturing the appearance of one. It could not, and the strongest evidence for that came from outside the original telescope altogether. Once other observatories, built differently, run by entirely separate teams, and operating on their own independent observing schedules, pointed their own dishes at the same patch of sky. They found the very same 16-day rhythm the first telescope had found, arriving on exactly the schedule it was supposed to. An artifact born from one particular telescope's habits should not show up, unprompted, in a completely different telescope's data. A real signal coming from a real object out in space should and does. When the team finally published their result in a paper that went through the same rigorous process of outside review every serious scientific claim must survive before it reaches print, the reaction inside the field was immediate. Other groups running their own radio telescopes wanted to see the pattern for themselves, and within a remarkably short stretch of time, several of them had. Confirmations arrived from observatories on more than one continent, each one independently pointing an antenna at the same small patch of northern sky and finding bursts arriving right on schedule, exactly where the 16-day cycle predicted they should. That kind of rapid, independent confirmation is rare in any field of science, and it happens, when it happens at all, only when a result is unusually solid. Within a year or two, what had begun as a single team's tentative finding had hardened into one of the most secure facts in the entire study of fast radio bursts, a period so well established that it is now used routinely to plan observing campaigns months in advance, telescopes booked and pointed at that patch of sky, specifically because the calendar says the signal should be waking up again soon. What was not settled, and remains genuinely open even now, was a stranger wrinkle that showed up almost as soon as astronomers started listening to the source, using instruments tuned to different parts of the radio dial. Radio waves, like visible light, come in a whole range of frequencies, the radio equivalent of the different colors that make up a beam of ordinary sunlight passed through a prism. Most of the original detections had come from a telescope tuned to a fairly narrow middle stretch of that radio spectrum. But other observatories soon turned their attention to the same source, using instruments built to listen at very different frequencies. Some tuned much higher, some tuned to some of the lowest radio frequencies ever used to catch a burst like this at all, using a continent-spanning array of antennas based in the flat farmland of the Netherlands. What those observatories found did not simply confirm the same 5-day active window at a different pitch. It found a window that shifted position and changed shape depending entirely on which frequency you happened to be listening at. Tuned to lower frequencies, the active window arrived slightly later within each 16-day cycle, and it stretched out wider, lasting longer than it did at higher frequencies. Tuned higher, the window arrived earlier and pulled in tighter, a narrower slice of time squeezed into an earlier part of the cycle. It was as though the source were not simply switching on and off once, but doing so in a slightly staggered fashion depending on the particular pitch of light you happened to be tuned to catch it with. Deep notes arriving on a different, later schedule than high ones. No one has ever offered a fully satisfying explanation for why that should be true, and it is worth sitting with that honestly rather than rushing past it. A handful of researchers have proposed mathematical descriptions that can reproduce the general shape of the effect. Models built around the idea that whatever region of space is actually producing these bursts is somehow more transparent to certain frequencies at certain points in the cycle than at others, letting some colors of the signal through earlier or more easily than others. But a description that can reproduce a pattern mathematically is not the same thing as a true physical explanation for why that pattern exists in the first place, and none of the proposals put forward so far have been confirmed as the genuine underlying cause. For now, the honest scientific position is simply this: the active window is not just a matter of on and off. It is a matter of on and off that quietly rearranges itself depending on which frequency you are tuned to, a level of intricacy that very few natural processes are known to produce, and one more layer of behavior that any eventual explanation for this signal will eventually have to account for. The range of frequencies involved in mapping out this shifting window was genuinely enormous by the standards of radio astronomy. At the highest end, telescopes tuned to catch the source at frequencies well suited to detecting it clearly and cleanly. At the lowest end, an array of antennas spread across the flat countryside of the Netherlands pushed down into territory so far toward the bottom of the usable range that no fast radio burst of any kind had ever been confidently detected there before. That in itself was a small victory worth pausing over. Radio waves at the very lowest frequencies are the hardest of all to catch cleanly, since they scatter and smear more severely on their long journey through the thin gas that fills the space between stars and between galaxies alike, arriving blurred and weakened in a way that higher frequencies mostly avoid. Managing to catch a clean, confirmed burst from this source at such stubbornly low frequencies was itself a meaningful technical achievement, and it only deepened the puzzle once astronomers compared what they found there against what higher frequency telescopes had already recorded. The window was not just present at both ends of that enormous range. It was different at both ends, shifted later and stretched wider down at the bottom, pulled earlier and squeezed tighter up toward the top, a graded, continuous kind of behavior, rather than a simple difference between two fixed settings. That discovery has since become a genuinely practical tool rather than simply an academic curiosity. Astronomers planning a fresh observing campaign on this source now know to schedule their higher frequency instruments slightly earlier in each 16-day cycle, and their lower frequency instruments slightly later, timing each observation to match the window's known drift, rather than simply watching continuously and hoping to get lucky. It is a strange kind of achievement, being able to predict precisely when and in what manner a distant signal will most likely appear, down to the day and the pitch, without having the faintest idea what is actually producing it, or why it behaves this way at all. Discoveries this strange invite an obvious question, one that is worth answering plainly rather than letting it linger unaddressed. If a source behaving with this kind of calendar precision is this unusual, how many others like it are actually out there? The honest answer, even today, is remarkably few. In the years since this particular signal revealed its rhythm, astronomers scanning the sky have confirmed only 2 other sources anywhere that show anything resembling true, repeating periodicity. One of them, The very first repeating burst ever discovered, back in the Arecibo data mentioned earlier in this story, was eventually found to have a period of its own, a much longer one, somewhere in the neighborhood of 157 days between active stretches, nearly 10 times the length of the cycle described here. Another, identified more recently and traced to a quiet, aging galaxy, unlike almost any other fast radio burst host studied so far, showed a period closer to 126 days. Both discoveries mattered enormously, each one confirming that this kind of long, structured rhythm was not simply a fluke belonging to a single strange object, but a genuine category of behavior that at least a few of these sources are capable of. And yet, out of well over 800 fast radio bursts confirmed to date, only a small fraction have ever been observed to repeat at all, and among that already narrow group, these three sources remain the only ones with a period precise enough and well established enough to set a calendar by. Whatever is producing this kind of behavior, it is clearly not the ordinary state of affairs for objects of this kind. It is closer to a rare specialty, 3 known cases scattered across the entire observable sky, each one presumably shaped by conditions unusual enough that most fast radio bursts never develop anything like it at all. It is worth adding one honest caveat here, the kind of caveat careful scientists insist on including, even when it complicates an otherwise tidy story. The fact that only 3 sources have ever shown confirmed periodicity does not necessarily mean periodicity itself is vanishingly rare among repeating fast radio bursts generally. Finding a period requires exactly the kind of patient, years-long monitoring described earlier in this story. Dozens of bursts, gathered over a long enough stretch of time to make the folding technique meaningful. Most known repeaters have never been watched anywhere near that closely, simply because there are far more of them than there is available telescope time to track them all in such detail. It remains entirely possible that other repeaters out there keep their own private calendars, cycles that have simply never been caught, for lack of anyone watching closely enough and long enough to notice. What can be said with real confidence is narrower, but still remarkable. Among the handful of sources studied carefully enough to answer the question one way or the other, this one, along with its 2 now confirmed cousins, are the only ones that have passed the test. None of this came together as neatly, in practice, as a tidy folded timeline might suggest. Telescopes do not watch the sky without interruption, even ones built specifically to stare at the same patch of it every day. Equipment needs maintenance. Storms roll through. Observing time gets shared among competing projects, each with its own claim on a limited number of hours. The real record of detections from this source was, inevitably, full of gaps, stretches of days or weeks where nobody happened to be watching closely enough to say for certain whether the source had been active or silent. Finding a genuine 16-day rhythm inside a record that incomplete is considerably harder than finding one in a perfect, unbroken stream of nightly observations, and it is part of why the astronomers involved insisted on gathering so many confirmed bursts, more than 3 dozen, before they were willing to trust the pattern at all. A shorter, patchier record might easily have produced a false positive, a coincidental cluster of dates that looked like a rhythm but was not. It took real patience and a genuinely large sample gathered across more than a full year before anyone was willing to put their name to the number 16.35 and call it settled. It is tempting, once a rhythm this precise has been confirmed, to feel as though the mystery has essentially been solved, that finding the beat is the same thing as understanding the drummer. It is not, and it is worth being completely clear about that distinction before going any further. Knowing that a source repeats every 16.35 days tells you a great deal about how to observe it, when to point a telescope at that patch of sky, and when to leave the instrument pointed elsewhere. It tells you almost nothing about what the source actually is. What kind of object out there could possibly produce a burst of that scale, let alone one obedient enough to keep time this precisely for years on end? A calendar tells you when something happens. It does not tell you why. And the honest state of the science, even with a period measured down to a fraction of a day and a duty cycle mapped out in careful detail, is that the why remained, at this point in the story, entirely up for grabs. Astronomers had proven, beyond any reasonable doubt, that something out among the stars was keeping remarkably careful time. They had not yet come anywhere close to identifying what that something actually was, and answering that question would require a very different kind of work than counting bursts and folding timelines, work that would eventually mean tracing this signal, precisely and painstakingly, back to the one exact galaxy it called home. There is a reason precise. Repeating cycles like this one tend to catch an astronomer's attention so completely, beyond simple novelty. In nature, genuinely regular rhythms, the kind measured in fixed days rather than vague tendencies, tend to trace back to one of only a couple of underlying causes. Something is spinning, steadily and predictably, the way a phonograph record turns beneath a needle, carrying the very same scratch or label marking back around to the same position once every single rotation, without fail. Or something is orbiting something else, circling a companion on a fixed path the way the planets circle the sun, each lap bringing it back through the same relative position again and again. Both spinning objects and orbiting objects are common throughout the universe, and both are entirely capable, in principle, of producing exactly the kind of on-again, off-again behavior recorded from this source. A window of visibility followed by a window where whatever process makes the burst possible is simply turned away or blocked or otherwise unavailable until the cycle brings it back around again. Which of those two general categories, if either, actually applies here, and what kind of object could be doing the spinning or the orbiting in the first place, is a question this video will turn to directly later. For now, what matters is simply that a precise period like this is not a dead end. It is a clue, and a specific one, narrowing an otherwise wide-open mystery down to a much smaller and more tractable set of possibilities. Confirming the rhythm, remarkable as it was, had not moved anyone a single step closer to answering the more basic question sitting underneath the entire investigation. Which particular corner of the universe was doing this? A precise period narrows the field of plausible explanations considerably, but it does not, on its own, point a finger at any specific galaxy, any specific type of star, or any specific physical process. For that, astronomers would need a completely different kind of tool, one built not for measuring time but for measuring position, capable of taking a signal from a single narrow patch of northern sky and narrowing it down with almost surgical precision to one exact location among the hundreds of billions of galaxies scattered across the observable universe. A tool built for measuring position rather than time already existed, and it lived in the very same small, tightly connected world of researchers that had been watching this signal from the beginning. Word of the confirmed 16-day rhythm reached Marcotte and his colleagues at almost the same moment it reached everyone else in the field. and for a researcher whose entire career had been built around tracking signals back to their exact point of origin, a source this reliable was close to a gift. Most fast radio bursts give you one chance, a single unrepeatable flash, gone before any second instrument can be brought to bear on it. This source, by contrast, now came with a schedule attached. Astronomers could look at a calendar, count forward, and know roughly which handful of nights out of any given month actually stood a reasonable chance of producing something worth chasing. That predictability turned an ordinarily hopeless kind of observation, waiting blindly for a burst that might never come again, into something closer to a planned expedition, and Marcote's team set about planning exactly that. The technique they relied on, the same continent-spanning method described earlier in this story, worked something like the old practice of fixing a ship's position at sea by taking bearings on the same radio signal from two or more separate listening stations at once. A single station can tell you a rough direction. Two or more stations, spread far enough apart and comparing notes precisely enough, can cross those directions against each other and mark an exact point on the map where they intersect. Radio operators used exactly this kind of cross-bearing to help guide ships and aircraft safely home for much of the 20th century, long before satellite navigation existed, and the underlying idea, listen from multiple widely separated points and compare what each one hears, is precisely what a network of linked radio telescopes does as well, only stretched across an entire continent instead of a coastline, and aim not at a passing airplane, but at a source many hundreds of millions of light-years away. On a single night in the middle of June of 2019, 8 separate radio telescopes scattered across Europe, coordinated by Marcote's Institute, turned themselves toward the same small patch of northern sky at precisely the same moment, waiting together for a burst that the calendar suggested had a reasonable chance of arriving. Among the dishes taking part was a true giant of the field, a single reflector in Germany measuring a full 100 meters across, one of the largest fully steerable radio telescopes ever built. Coordinating a night like this took months of preparation. Observatories that ordinarily serve dozens of unrelated research projects had to be booked in advance for one narrow overlapping window, their schedules aligned so that all 8 instruments would be listening at once, rather than at whatever hours happened to be convenient for each site individually. It is the kind of quiet, unglamorous, months-long logistical effort that never appears in a headline, and without which no single dramatic discovery in this story would have been possible at all. Making 8 independent telescopes act as one required more than simply pointing them all in the same direction at the same time. Each station recorded its own raw data continuously throughout the night, time-stamped against its own extraordinarily precise atomic clock, accurate enough to keep step with every other clock in the network to within a tiny fraction of a second. Only later, once all 8 recordings had been physically gathered together and processed side by side at a central facility, could researchers actually compare them, sliding one recording against another in tiny increments until the same burst, arriving at each station just an instant apart, lined up perfectly. That alignment, precise down to a fraction of a billionth of a second, is what ultimately let the team calculate the burst's position with such extraordinary accuracy, a piece of work that happens entirely after the fact, in a laboratory, long after the telescopes themselves have moved on to other targets. The bet paid off. There was no guarantee going into that night that anything at all would happen. The calendar suggested favorable odds. Nothing more. Telescopes across an entire continent sat pointed at the same small stretch of sky for hours, recording continuously, gathering nothing but ordinary background static that any radio receiver picks up as a matter of course. And then, at some point during that long quiet vigil, the signal arrived exactly as hoped, a fleeting burst of radio light captured simultaneously by every station in the network. There and gone within a thousandth of a second, indistinguishable to the naked ear from all the ordinary noise surrounding it, and yet carrying, buried inside it, everything the team needed to finally answer a question that had been open since the very first detection of this signal months earlier. Bursts arrived that night, recorded simultaneously by every station in the network, and in the weeks that followed, Marcotte's team combined those separate recordings with the same painstaking cross-referencing a navigator might once have used to fix a ship's position, comparing the exact fraction of a second each dish received the signal and using those tiny differences to sharpen a single vague direction into something close to an exact address. The result was a position in the sky precise enough, remarkably, to identify not just a general patch of stars, but a specific individual galaxy. And once that galaxy had been pinned down, the team turned to a very different kind of instrument entirely. A large optical telescope perched atop a dormant volcano in Hawaii, built to gather visible light rather than radio waves, pointed at the same coordinates. It produced a clear photograph of the culprit, and for the first time, astronomers were not simply listening to a mysterious signal from somewhere out in the dark. They were looking directly at a picture of its home. What that photograph revealed was a galaxy that, at first glance, might have looked almost reassuringly familiar. It was a spiral, broad and well-formed, its arms winding gently outward from a bright central bulge in the same general architecture as our own Milky Way, and it happened to be tilted nearly face onto Earth, presenting itself to Gemini's camera, the way a slowly turning pinwheel looks when you view it straight down its own axis, rather than edge-on. The galaxy was substantial, a genuine heavyweight rather than a small or unusual dwarf system, sitting at a distance researchers calculated at roughly 486 million light-years, based on how much its light had stretched and reddened on the long journey here. That distance is difficult to hold in the mind for long. Light, leaving that galaxy today, would not reach Earth until long after everyone currently alive has been gone for many, many lifetimes over. And the light captured in Gemini's photograph that night had already been traveling toward us since long before the first stone tools were shaped by human hands. And yet, on the scale astronomers use to measure the universe, 486 million light-years is, remarkably, considered close. Most confirmed fast radio bursts trace back to galaxies billions of light-years away, their light having set out on its journey before Earth itself had finished forming. This one, by comparison, was practically a neighbor. The precise spot the burst called home was not the galaxy's glowing central bulge, but a smaller, brighter clump out along one of its spiral arms, a region where new stars were actively being born, dense with the raw gas and young, hot stars that mark active stellar nurseries throughout the universe. Astronomers measured the burst's position as sitting just slightly offset from the very brightest heart of that stellar nursery, near enough to be clearly associated with it, but not dead center, a small detail that would later matter a great deal to researchers trying to work out exactly what kind of object might be responsible. That detail, a young, active stellar nursery rather than a quiet, settled part of the galaxy, carries real weight for anyone trying to guess what kind of object is actually responsible. Regions like this are where massive stars are born, live fast, and die young, collapsing within just a few million years into exactly the kind of dense, magnetized remnant capable of producing a fast radio burst in the first place. A location like this fits naturally with the idea of a relatively young compact object, one that has not had very much cosmic time to slow down or settle into old age. That detail will matter again later in this story, once the conversation turns to which kind of object might actually be producing this signal, since not every proposed explanation sits equally comfortably with a birthplace this young. It is worth pausing on how significant this particular localization actually was, and also on how the story around it has shifted somewhat since. This was only the second time in the entire short history of this field that astronomers had ever managed to trace a repeating fast radio burst back to a specific home galaxy at all. The first repeater ever confirmed, traced a few years earlier to a small, faint, irregular dwarf galaxy far across the universe, had already reshaped how researchers thought about where these signals might come from. This second success told a very different story. Rather than a small, unusual star-poor dwarf galaxy, here was a large, ordinary, well-formed spiral, broadly similar in scale to our own home galaxy, which meant that repeating fast radio bursts, whatever caused them, were clearly capable of arising in more than one kind of cosmic neighborhood. Taken together, these two examples told researchers something important about the entire category of repeating fast radio bursts, something that would have been impossible to know from either discovery alone. A single example might have been a fluke, a lone, unusual signal born from unusual circumstances. Two examples, drawn from such different kinds of galaxies, suggested instead that whatever produces a repeating burst is not tied to one single, narrow kind of cosmic environment. It can apparently arise in the sparse, metal-poor outskirts of a small dwarf galaxy, and it can also arise in the crowded, star-forming arm of a large, well-developed spiral not unlike our own. That diversity would go on to matter for every theory proposed afterward, since any successful explanation would eventually need to account for repeating bursts turning up in such different kinds of neighborhoods, rather than being tied to one specific, unusual set of galactic conditions. At the time of the announcement, this newly pinpointed source also carried another distinction. Given how close 486 million light-years is by the standards of this field, it was, for a while, described as the closest fast radio burst of any kind ever precisely located. That particular claim has not held up, and it is worth setting the record straight plainly, rather than repeating an outdated headline. In the years since, astronomers using this same kind of continent-spanning technique traced a different burst, one that never developed anything resembling a repeating rhythm at all, to a cluster of extremely old stars orbiting within a much nearer galaxy, at a distance of only a few million light-years, dramatically closer than the source at the center of this story. That discovery quietly took over the record for sheer proximity, and it likely will not be the last to do so as instruments improve and searches widen. But a narrower, more specific title has never changed hands. Among the small and exclusive group of fast radio bursts that repeat on a genuine, confirmed, measurable calendar, the kind of signal at the very heart of this story, this one remains, to this day, the closest such source ever found. The two other confirmed periodic repeaters mentioned earlier both sit dramatically farther away, hundreds of millions of light years beyond even this galaxy's own considerable distance. Whatever is producing a clockwork rhythm like this one, this particular example, remains the nearest astronomers have ever been able to study it up close. Knowing exactly where the signal lived did not, on its own, answer the question that mattered most. A street address tells a curious neighbor where to look, not who actually lives inside. With a precise location finally in hand, researchers could begin asking a much sharper version of the central question that had been building since the very first burst was noticed years earlier. What kind of object, sitting in that star-forming clump, in that spiral arm, in that distant galaxy, could possibly produce a burst of radio light this powerful, and do so on a schedule precise enough to set a calendar by? Three broad answers have dominated the conversation ever since, each one grounded in real, established astrophysics, each one capable of explaining a meaningful piece of the puzzle, and not one of them yet confirmed beyond doubt. The first, and in some ways the most intuitive, candidate involves company. Picture two stars locked together in a long, looping orbit around each other, the way many stars throughout the galaxy are paired rather than solitary. One member of this hypothetical pair is not an ordinary star at all, but the collapsed, city-sized remnant of one, packed so densely that a single teaspoon of its material would outweigh a mountain, and wrapped in a magnetic field of a strength no laboratory on Earth has ever come close to producing, the kind of object astronomers call a magnetar. The other member of the pair is a genuine giant, a massive, hot, young star, the type that burns through its fuel quickly and sheds a constant, powerful wind of charged particles out into the space around it. Stars of this particular type, sometimes further along in their evolution, to have built up a broad, spinning disk of gas around their own equator, are common enough throughout the galaxy that pairing one with a compact, collapsed remnant is far from an exotic proposal. Astronomers see binary systems built from exactly this kind of mismatched pair, a massive, living star locked in orbit with the dead, dense remnant of another star, in a number of other well-documented settings throughout the galaxy, which is part of what makes this particular explanation feel so plausible on its face. As the compact remnant swings through its orbit, sometimes it passes close to its giant companion, and sometimes it swings out farther away. When it is near, the theory goes, the dense, charged wind pouring off the companion star can absorb or scatter the radio waves, trying to escape from the compact object, muffling the signal almost entirely, the way a heavy fog can swallow the beam of a searchlight before it ever reaches the far shore. When the compact object swings out to a wider part of its orbit, clear of the thickest part of that wind, the signal can escape freely and reach Earth unobstructed. On this view, the 16-day rhythm is not a rotation or a wobble at all, but an orbital period, the time it takes the pair to complete one full circuit around each other, alternating between hidden and visible as the geometry of their orbit carries the compact object in and out of its companion's sheltering wind. This companion star model has one particular strength that neither of the other two explanations shares quite as naturally. It offers a genuinely physical reason for the strange, frequency-dependent behavior of the active window described earlier in this story. A dense stellar wind does not block every radio frequency equally. Lower frequencies are absorbed and scattered far more easily by charged, ionized gas than higher frequencies are. In much the same way that thick fog swallows a dim yellow lamp long before it swallows the sharper beam of a modern headlight. If the compact object's radio emission has to fight its way out through a changing thickness of stellar wind as it moves along its orbit, lower frequencies would naturally struggle to escape until the geometry became more favorable, arriving later in the cycle and taking longer to fade back out, exactly the pattern observed. It is an elegant explanation precisely because it accounts for two separate mysteries: the basic switching on and off and the odd behavior across different frequencies, using a single underlying physical picture. That elegance is a real point in its favor, though elegance alone has never been sufficient proof for anything in careful science, and the companion star remains, for now, a proposal rather than a confirmed fact, one that researchers continue testing against every new observation that comes in. The second candidate removes the companion star from the picture entirely and looks instead at the compact object all by itself. Neutron stars, including the especially strongly magnetized ones known as magnetars, spin, often extremely quickly, sometimes completing many full rotations in a single second. But a spinning object does not always spin in a perfectly smooth, stable fashion. Picture a child's top, given a slightly off-center spin rather than a clean, balanced one. Instead of turning cleanly upright, it wobbles as it spins, its axis slowly tracing out a small circle in the air, even as the top itself continues turning rapidly. Astronomers call this kind of wobble precession, and there is no reason, in principle, why a magnetar could not do something similar, its own rotation axis slowly tracing a wide, lazy circle over the course of days or weeks, even as the star itself spins many times each second. If the star's beam of radio emission is fixed to that slowly wobbling axis, rather than pointed straight out along a perfectly stable pole, it would only sweep across Earth's line of sight during part of each wobble, appearing to switch on and off on whatever time scale the wobble itself completes. In this case, once every 16 days. This precession model carries real appeal because wobbling, spinning objects are a familiar and well-understood piece of physics, seen throughout nature at every scale, from a child's top to the slow, multi-thousand-year wobble of the Earth's own axis. But the idea runs into a genuine complication when tested against real magnetars that astronomers have actually managed to observe wobbling in this way, closer to home within our own galaxy. In at least one such case, a strongly magnetized neutron star that began precessing visibly after a violent outburst, researchers watched the wobble fade and settle back down within just a few months, the star's own internal structure apparently damping out the motion far too quickly for it to explain a rhythm that has now held steady, without any sign of slowing, for years on end. That does not rule the idea out entirely. Some researchers argue that a magnetar with a different internal structure or a different strength of magnetic field might sustain a much longer-lived wobble than the one example observed so far, and the mathematics involved leaves room, if barely, for a wobble that persists for years rather than months. But it is a real strike against the simplest version of this explanation, and one that any full defense of the wobbling magnetar picture now has to answer directly rather than sweep aside. The third candidate keeps the compact object alone, once again, with no companion star and no wobble, and instead asks a more basic question. What if the 16-day period is not a wobble layered on top of ordinary fast rotation, but the star's actual rotation itself slowed down to a degree that would be almost unheard of among objects of this kind? Most magnetars complete a full rotation in a matter of seconds, some in less than a single second, spinning far faster than almost anything else known in nature relative to their size. A magnetar, rotating once every 16 days, would be almost absurdly slow by comparison. The difference between the sweeping second hand on a pocket watch and the nearly motionless hour hand on the very same face, both technically still moving, but on time scales that barely resemble each other at all. For a magnetar to slow down this dramatically, it would likely need to be extremely old by the standards of these objects, having spent a very long stretch of time gradually bleeding away its own rotational energy through the same powerful magnetic field that makes it a magnetar in the first place, acting almost like a natural brake applied continuously over a very long span of time. If some magnetars really can age into this kind of extreme, slow rotation, and if their magnetic activity can somehow still produce bursts of radio light only during a narrow portion of each slow rotation, this model would explain the basic switching on and off without needing to invoke either a companion star or an unstable wobble at all. It is, in some ways, the simplest of the three ideas. But simplicity has not made it any easier to confirm, since directly measuring the rotation of a neutron star that faint, that far away, remains well beyond the reach of any instrument currently in use. There is also a natural tension worth noting between this idea and the birthplace described earlier in this story. An old, slowly spinning remnant is, almost by definition, not a newborn one, and this particular source was found sitting inside an active region where young stars are still being formed. That tension is not a fatal flaw. Even magnetars, considered old by the standards of these objects, are still, by any ordinary measure, extremely young, often only a few thousand years removed from the explosion that created them, a blink of an eye against the age of the galaxy surrounding them. But it is one more thread that any full explanation involving this idea will eventually need to weave together with everything else already known about where this signal actually lives. Telling these three possibilities apart from each other is a genuinely difficult observational problem, and it is worth understanding why, rather than simply accepting that the question remains open. All three candidates predict roughly the same basic behavior: a source that switches on for part of its cycle and off for the rest, which means the 16-day rhythm itself, however precisely measured, cannot distinguish between them on its own. Confirming or ruling out a companion star would ideally mean detecting that star directly, spotting its own separate light mixed in with the burst's home galaxy, an enormously difficult task, given how far away the entire system sits, and how faint any single ordinary star becomes at that distance. Confirming a wobble would mean tracking subtle, repeatable changes in the exact polarization and pointing of the radio waves themselves over the course of many complete cycles, the kind of long-term, painstaking measurement that takes years to accumulate. Confirming slow, old-age rotation would mean somehow measuring the compact object's spin directly, a feat that has never yet been accomplished for any magnetar this far from Earth. Each path forward is difficult in its own particular way, and none of them offers a quick answer. What researchers have instead relied on is a slower, more indirect kind of evidence, watching not the bursts themselves but the space immediately surrounding the source, looking for subtle changes in how that space bends and twists the radio waves passing through it on their way to Earth, changes that might, indirectly, favor one explanation over the other two. None of these three explanations has been ruled out, and none has been confirmed. Each accounts for part of what astronomers have measured. None accounts for all of it cleanly on its own, without leaning on an assumption that has not yet been directly tested. And in the years since these three candidates first entered the conversation, a new and unexpected piece of evidence has emerged from the source itself, evidence involving the way its magnetic surroundings appear to be quietly, slowly changing over time, in a manner that none of the three original proposals had fully anticipated when they were first put forward. That evidence does not settle the argument between a companion star, a wobbling axis, and an old, slow-spinning remnant. If anything, it complicates all three at once, and untangling exactly how is where this story turns next. The evidence that complicated all three explanations at once did not come from watching the bursts themselves, but from paying close attention to something far more subtle: the faint fingerprint, the empty space between here and that distant galaxy leaves on the radio light passing through it. Radio waves, like light of any kind, vibrate as they travel, oscillating in a particular direction, a particular plane, the way a jump rope shaken from one end whips up and down along a single flat sweep, rather than corkscrewing wildly in every direction at once. When that kind of wave passes through a region filled with charged particles sitting inside a magnetic field, its plane of vibration does not stay fixed. It twists, gradually, the longer and denser the magnetized material it has to cross. Astronomers can measure that twist precisely, and because the amount of twisting depends directly on how much magnetized material the light passed through, the measurement works something like an odometer, not for distance traveled, but for how much charged, magnetized gas has been pushed through along the way. A small twist suggests a light, sparsely magnetized path. A large twist suggests something denser and more strongly magnetized, sitting somewhere between the source and Earth. Measuring that twist accurately is itself a demanding piece of work, requiring astronomers to capture not just that a burst arrived, but the precise angle at which its radio waves were oscillating when they did. Information easily lost or blurred unless an instrument is built and calibrated with exactly this kind of measurement in mind. Only a handful of the telescopes involved in this story were equipped to make measurements this fine, and doing so required comparing many individual bursts against each other, gathered over separate observing campaigns months apart, before researchers could speak with any confidence about how the twist itself might be changing over time rather than simply varying at random from one burst to the next. For most fast radio bursts, astronomers measure this twist once, note it down, and move on, treating it as a fairly stable property of the particular patch of space the signal happens to be crossing. For this source, that assumption did not hold. When researchers went back and compared measurements taken only months apart, in the year 2021, they found that the twist itself had changed, and changed by a striking amount, growing stronger by something in the neighborhood of 40% in less than a year. That is not the kind of shift you would expect from light simply crossing the same quiet stretch of largely empty space, month after month, on its way here. Empty space, however vast, tends to leave a fairly constant fingerprint on the light passing through it. A fingerprint that changes this much, this quickly, points towards something considerably more active and more localized, a small pocket of unusually dense, unusually magnetized material, sitting extremely close to the source itself, a pocket whose properties appear to be shifting in real time, on a timescale of months, rather than the millions or billions of years ordinary interstellar space tends to change on. More recent work has pushed this observation even further, and it is worth presenting carefully because the science here has not yet fully settled. A study published in the year 2025, using observations gathered from a large radio telescope array in India, reported tentative evidence that the twist may have done something even stranger than simply growing stronger. It may, at some point, have reversed direction entirely, flipping from one sense of rotation to the opposite sense, the way a screw thread might appear to reverse if you suddenly found yourself looking at it from the other side. The researchers involved were careful, appropriately careful, not to present this as a settled fact. They described it as a tentative detection, one that future observations would need to confirm before anyone could treat it as established. If it does hold up, it would make this only the third fast radio burst source ever observed to show this kind of reversal, an exceptionally rare piece of behavior, even within an already exceptionally rare category of signal. For now, the honest position is that the twist is growing and changing in ways that go beyond ordinary expectation, and that a full reversal remains a genuine possibility rather than a confirmed result. Either way, growing or reversing, the underlying message is the same. Something in the immediate neighborhood of this source is magnetically alive, changing on a timescale that is fast by cosmic standards and yet still measured in months and years rather than days. And it is precisely that timescale, rather than the existence of the changing magnetism itself, that ended up complicating every explanation described earlier in this story, rather than confirming any single one of them outright. None of this work has happened in one place or within one single research group. Teams in Canada continue monitoring the source using the same wide-eyed telescope that first noticed it flickering back in 2018. Teams in Europe continue refining the precise location using the same continent-spanning technique that first traced it to its home galaxy. Teams working with large radio arrays elsewhere have contributed the careful measurements of its shifting magnetism described in this story. No single observatory and no single country holds this signal exclusively. It has become, quietly, a shared international puzzle, each new paper building on the last, each new observing campaign, adding one more data point to an investigation that has already stretched across the better part of a decade, with no sign of concluding cleanly anytime soon. Consider what this evidence does for the idea of a companion star locked in orbit with the compact remnant described earlier as offering the cleanest explanation for the way the active window shifts and narrows depending on frequency. A changing, strengthening magnetic environment fits that picture beautifully at first glance. A massive companion star constantly sheds a wind of charged, magnetized particles, and if the compact object were plowing through an increasingly dense pocket of that wind, exactly this kind of growing twist is more or less what you would expect to see. But there is a catch, and it is a serious one. If this changing magnetism really were tied to the same orbital motion responsible for the 16-day rhythm, you would expect the twist to rise and fall in step with that same 16-day clock, growing stronger as the compact object swings closer to its companion and weakening again as it swings away, cycle after cycle, in lockstep with the bursts themselves. That is not what the data shows. The twist changed steadily over the better part of a year, far too slowly to be tracking a companion star being orbited once every 16 days. Whatever is producing this slow magnetic drift, it is evidently not completing a full circuit every 16 days, the way the simplest version of the companion star story would require. This does not rule out a companion star altogether. It does something more interesting. It suggests that if a companion star is involved at all, its orbit around the compact object must be considerably longer than 16 days, stretching across months or years, rather than completing a full circuit every 2.5 weeks. Under that revised picture, the 16-day rhythm governing when bursts appear and the much slower drift in the source's magnetic surroundings would not be the same clock at all. They would be two entirely separate periodic behaviors, operating side by side on the very same object, on wildly different timescales, for reasons that have nothing directly to do with each other. That distinction is worth sitting with for a moment, because it is easy to let two different rhythms blur together into one tidy story, when in fact they may not belong together at all. Consider something as familiar as the planet beneath your own feet. Earth turns on its axis once roughly every 24 hours, giving you day and night, morning and evening, a rhythm so constant you rarely think about it at all. Earth also completes a much longer journey, one full orbit around the Sun roughly once a year, giving you spring, summer, autumn, and winter, an entirely different rhythm, operating on an entirely different timescale. Nobody looks at a calendar in December and tries to explain the arrival of winter by pointing to the fact that the sun rose that morning at its usual hour. They are simply two separate clocks, ticking away at their own separate paces, sharing the same planet without being tangled up in each other's mechanics. It now looks entirely possible that something similar may be happening here, a fast, precise 16-day clock governing exactly when this source speaks, and a much slower, separate rhythm, possibly tied to an orbiting companion, possibly tied to something else entirely, governing how its magnetic surroundings drift and change. Two clocks on one object, keeping entirely different kinds of time. It is a strangely comforting thought, in its own way, once you sit with it for a moment. The earth beneath you keeps two honest clocks running at once without any confusion or contradiction, one fast, one slow, each faithfully doing its own separate job. There is no reason to assume the universe only knows how to keep one kind of time on any given object. A neutron star, or whatever this particular source turns out to be, may simply be doing what plenty of ordinary things already do, running more than one rhythm simultaneously, each one real, each one measurable, neither one cancelling out or explaining away the other. That same complication reaches the wobbling magnetar explanation as well, though in a different way. A slow precession, the gradual wobble of a spinning object's axis, was always framed as a way to explain the 16-day switching itself, not the slower magnetic drift observed since. In principle, the two could coexist peacefully, a wobble producing the 16-day rhythm, while some separate, unrelated process drives the changing magnetism nearby. But the discovery of a genuinely active, evolving magnetic environment sitting close to the source does add a small mark against the simplest version of the precession story, since that version generally pictures a single, isolated compact object, largely alone in space, with little reason to expect its immediate surroundings to be this magnetically busy and changeable in the first place. An isolated, precessing magnetar can be rescued from this complication, researchers point out, if it turns out to be embedded in a dense, leftover cloud of material from its own violent birth, material that could plausibly still be shifting and settling years after the fact. But that rescue requires an additional assumption the original idea did not originally need, and every additional assumption a theory requires makes it that much harder to consider the simplest or most likely explanation on offer. The old, slowly rotating magnetar explanation fares a little better against this particular piece of evidence, mostly because it never made any strong prediction about the surrounding magnetism to begin with. An ancient, extremely slowly spinning compact object, sitting quietly for many thousands of years, was never expected to be orbited by anything in particular, and its magnetic surroundings could plausibly change for all sorts of independent reasons having nothing to do with the object's own rotation. That flexibility is not, strictly speaking, a point in its favor. A theory that can comfortably absorb almost any new piece of evidence without being tested by it is, in its own way, a weaker theory than one that makes sharp, specific, checkable predictions, even when some of those predictions turn out to be wrong. Science tends to trust ideas that stick their neck out and can be proven false, more than ideas flexible enough to explain nearly anything. The most recent line of investigation has focused less on the twist itself and more on a closely related property, the precise angle at which the radio waves are polarized as they arrive, and how that angle shifts, subtly, from one burst to the next, across the full 16-day cycle. Each of the three leading explanations makes a slightly different prediction about how that angle ought to behave. A wobbling axis should produce a polarization angle that swings through a smooth, repeating arc as the star's beam sweeps across Earth's line of sight. A companion star's absorbing wind should leave a different signature, tied more closely to geometry than to the compact object's own orientation. An old, slowly rotating magnetar should behave differently still. Researchers have begun the painstaking work of measuring this angle across dozens of individual bursts, comparing the pattern against each of the three predictions in turn, hoping to find a clear enough match to finally rule two of the three explanations out. As of the most recent published analysis, the comparison remains inconclusive, close enough to more than one prediction that no confident verdict has yet been possible, though the researchers involved have been clear that they consider the approach promising and that further observations, gathered patiently over the coming cycles, may eventually settle the matter. Taken all together, the honest state of the science, as of the most recent research available, is this. Astronomers know, with a very high degree of confidence, that something out in that spiral arm of that distant galaxy switches on for roughly 5 days out of every 16 and off for the rest, on a schedule precise enough to plan observations around months in advance. They know that active window shifts and narrows depending on which radio frequency you are tuned to listen with, in a way no one has yet fully explained. They know the immediate magnetic surroundings of the source have grown noticeably more twisted over the span of less than a year, and may, tentatively, have reversed direction entirely, evidence of a genuinely dynamic, evolving environment, rather than a calm, unchanging one. They have 3 serious, well-reasoned candidates for what kind of object might be responsible: a companion star, a wobbling axis, an old and extremely slow rotation, and every one of those 3 candidates now carries at least one piece of evidence sitting awkwardly against it. As of this telling, no tipping point toward any single explanation has arrived. The question remains, quite genuinely, open. It is even possible, researchers acknowledge, that the true picture involves more than just 2 clocks running side by side. A wobble and a slow, evolving magnetic environment are not mutually exclusive ideas, and nothing rules out some combination of more than one of the three candidates working together, an old, precessing magnetar embedded within the leftover debris of its own birth, for instance, rather than any single tidy explanation standing entirely alone. Nature has a long history of turning out to be more tangled than the first, cleanest hypothesis assumed, and this signal may simply be another entry on that list. There is a particular kind of achievement buried inside that open question, one easy to overlook if you are only listening for a tidy final answer. Stop and consider, for a moment, how strange this actually is when held up against everyday experience. If a neighbor's porch light flickered on the very same nights each month, you would not rest until you had worked out why, and in all likelihood, you would manage it within a week or two of paying attention. A loose wire, a faulty timer, a motion sensor triggered by something passing through the yard. Ordinary mysteries, the kind everyday life presents constantly, tend to yield fairly quickly to patient attention because the range of plausible causes is small and the objects responsible are close enough to examine directly. This mystery has already resisted years of attention from some of the most capable instruments and most careful minds currently working in astronomy, not for lack of effort and not for lack of data, but because the object responsible sits hundreds of millions of light years away, far too distant to examine directly by any means available today, leaving researchers to reason their way toward an answer. Using nothing but the second-hand evidence radio waves happen to carry with them on the long journey here. Consider everything that had to happen for this story to reach the point it has reached tonight. A telescope with no moving parts, built to study hydrogen rather than radio bursts, had to notice a flicker repeating from one small patch of sky. Researchers had to resist the urge to call that flicker ordinary, and instead lay years of scattered dates end to end, testing one possible rhythm after another, until a single 16-day cycle locked everything into place. A team spread across an entire continent had to coordinate 8 separate telescopes down to a fraction of a billionth of a second on a single night to trace that rhythm back, not just to a general direction in the sky, but to one particular star-forming clump inside one particular spiral galaxy, sitting so far away that its light had already been crossing the emptiness of space for longer than human beings, or anything resembling them, have existed to look up and wonder about it. And still, after every one of those genuine, hard-won triumphs, the most basic question anyone could ask about this signal, what is actually producing it, remains unanswered. That gap between knowing precisely where something is and knowing precisely what it is says something worth sitting with quietly. It is tempting to think of scientific progress as a single, steady climb toward complete understanding, each new discovery closing a little more distance toward some final, total picture of how the universe works. This signal tells a more honest and, in its own way, more interesting story. Locating something and understanding it are two entirely different achievements, built from entirely different kinds of work, and a civilization can become extraordinarily skilled at the first while remaining genuinely, humbly stuck on the second. Humanity can now point a network of instruments across an entire continent, catch a flash of light lasting 1,000th of a second, and trace it back to one exact spiral arm in one exact galaxy, hundreds of millions of light years away, an act of precision that would have sounded like pure fantasy to any astronomer working only a few generations ago. And that same humanity still cannot say, with any real confidence, what is actually sitting in that spiral arm doing the work. Both of those things are true at once, and neither one cancels the other out. The precision is real. The mystery is also real. Progress, it turns out, does not always mean answers arriving on schedule to match the questions. Sometimes it means the questions themselves getting sharper, more specific, more exactly located, long before any answer catches up to meet them. There is something almost restful in that realization if you let it settle rather than fight it. Most of us spend a great deal of ordinary life waiting on questions we cannot yet answer about our health, our families, the shape of years still ahead of us, learning slowly that patience and uncertainty are not failures to be corrected, but simply part of what it means to live inside an unfinished story. Astronomy, for all its telescopes and calculations, turns out to run on exactly the same terms. Compare that, for a moment, to the kinds of mysteries that used to keep earlier generations of astronomers awake at night. The true nature of the fuzzy patches once called nebulae, later revealed to be entire separate galaxies, or the true source of the steady warmth pouring off our own star. A question that stood unanswered for the better part of human history, until nuclear physics finally supplied the missing piece in the 20th century. Those mysteries, too, were built entirely from honest observation rather than guesswork, and they too resisted explanation for a very long time before finally yielding to some combination of better instruments, better theory, and simple patience. There is no guarantee this particular mystery will resolve on any similar timeline. There is also no reason to expect it will not, eventually, join that same long and honorable list of things that once seemed permanently unexplainable and did not, in the end, stay that way forever. Even without a final answer, this single source has already reshaped how researchers think about fast radio bursts as a whole. Before its rhythm was confirmed, most researchers assumed periodicity, if it existed at all, would be rare to the point of irrelevance. Now, 3 confirmed examples exist, and searches specifically designed to look for hidden rhythms in other repeaters have become a standard part of how new sources get studied, directly because of the precedent set here. Before its location was pinned down, some researchers wondered whether repeating bursts might be tied to one narrow type of host galaxy. Now, having found this signal sitting inside a large, ordinary spiral alongside an earlier example found in a small, unusual dwarf, that assumption has been set aside for good. A mystery that has not yet answered its own central question has, in the meantime, quietly rewritten the rules for how an entire field studies every other signal like it. Somewhere in that distant spiral galaxy tonight, whatever it actually is, that source is likely moving through its own private calendar, some stretch of its 16-day cycle quietly ticking past whether or not anyone on Earth happens to be listening. It has kept that appointment faithfully since long before anyone here knew it existed, and it will very likely go on keeping it long after every telescope currently trained on that patch of sky has been retired and replaced by something better. Astronomers will keep watching. New instruments, more sensitive than anything available tonight, are already being planned, and each one will add a little more detail to the picture, a little more precision to the timing, a little more nuance to the debate between a companion star, a wobble, and an old, slow spin. Whether any of them will finally settle the question is not something this story can honestly promise. There is a kind of peace available in that thought, if you let yourself sit with it rather than resist it. Not every question needs to be answered tonight, or this year, or even within your own lifetime, for it to be worth carrying with you. Somewhere, above you, right now, A source hundreds of millions of light years away may or may not be entering its 5 days of activity, following a rhythm it has kept since long before anyone on Earth was listening, indifferent to whether you understand it. Content, simply to keep its own appointment regardless. What can be said, plainly and without exaggeration, is only this. Somewhere, out there, a signal that nobody can yet explain is still, tonight, keeping remarkably careful time, and the fact that we know precisely where to listen for it, precisely when it is likely to speak, and still cannot say for certain why, is not a failure of modern astronomy. It is exactly what real scientific discovery looks like while it is still underway, long before anyone has the luxury of calling it finished. Sleep now. Somewhere above, a patient clock keeps its own quiet count.